Hey guys, welcome back to another episode of the Wikiclick podcast. As always, this is Kyle Hellcamp. Some of you may have noticed my absence. Just joking, I don't have any viewers for this. This podcast is basically just a labor of love. Helps me learn. It helps me get good at English. But hypothetically, if I had viewers, some of you might have noticed that I've been away for a while. I've been on some adventures. So after today, I'll only be 2 podcasts behind, and I plan to knock those out bam, bam, one after the next. I do need a backlog for this, I think, in order for it to be beneficial. Today, I'm going to start with photovoltaics, which are it's the term that uses to let's restart this again, trying to get good at English. Photovoltaics being the term used to describe how light turns into electricity. Solar panels use this. The reason I'm starting with that, photovoltaics and energy in general are highly interesting to me. And here's hoping we can go one podcast without delving into the past. So let's get started here. Photovoltaics is a term which covers the conversion of light into electricity using semiconducting materials that exhibit the photovoltaic effect, a phenomena studied in physics, photochemistry, and electrochemistry. A typical photovoltaic system employs solar panels, each comprising a number of solar cells, which generate electrical power. PV installations, being, photovoltaic, may be ground-mounted, rooftop-mounted, or wall-mounted. The mount may be fixed, or use sky tracker to follow the sun across the sky. Solar photovoltaicism, solar PV, has specific advantages as an energy source. Once installed, its operation generates no pollution and no greenhouse gas emissions. It shows simple scalability in respect to power needs, and silicon has large availability in the Earth's crust. PV systems have the major disadvantage that the power output works best with direct sunlight, so about 10 to 25% is lost if a tracking system is not used. And tracking systems, if you've ever seen a time-lapse of those, you'll see solar panels in the desert, and they will swivel as the sun goes around. They will track the sun. They're not too hard to build, at least on a small scale. I've messed around before with robotics, and it's not too difficult to make a light-directed kind of sensor pointing in one direction. On a large scale, however, in terms of industrial energy gathering, I'm sure that the needs are a lot greater, especially in a desert condition where you're going to get sand and grit and all of the fine workings. Dust, clouds, and other obstructions in the atmosphere also diminish the power output. Another important issue is the concentration of the production in the hours corresponding to main isolation, which do not usually match the peaks in demand in human activity cycles. Essentially, that was a long-winded way of saying battery storage. It's hard to store that power, and power is typically generated during the day when we use a lot less of it. At night, you need it for lights, you need it for heating or cooling, which I suppose you need during the day as well, but unless current societal patterns of consumption electrical networks adjust to the scenario, electricity still needs to be stored for later use or made up by other power sources, usually hydrocarbons. Okay, so scrolling down here to the article, let's look up at let's go into current developments. For best performance, terrestrial PV systems aim to maximize the time they face the sun. Solar trackers achieve this by moving PV panels to follow the sun. The increase can be by as much as 20% in winter and by as much as 50% in summer. Static mounted systems can be optimized by analysis of the sun path. Panels are often set to latitude tilt, an angle equal to the latitude, but performance can be improved by adjusting the angle for summer or winter. Generally, as with other semiconductor devices, temperatures above room temperature reduce the performance of photovoltaics, so keeping them cool is probably kind of an issue. That's interesting to note. A number of solar panels may also be mounted vertically above each other in a tower if the zenith distance of the sun is greater than 0, and the tower can be turned horizontally as a whole, and each panel additionally around a horizontal axis. In such a tower, the panels can follow the sun exactly. Such a device may be described as a ladder mounted on a turntable disc. Each step of that ladder is the middle axis of a rectangular solar panel. In case the zenith distance of the sun reaches 0, the ladder may be rotated to the north or the south to avoid a solar panel producing a shadow on a lower solar panel. So what it's saying is, here is your tower, and you have a panel here, and here, and here, and here, and the tower will adjust itself, and the solar panels will adjust themselves. Another recent development involves the makeup of solar cells. Perovskite is a very inexpensive material which is being used to replace the expensive crystalline silicon, which is still part of standard PV cell build to this day. Michael Greitzel, director of the Laboratory of Photonics and Interfaces at EPFL, says, "Today efficiency has peaked at 18%, but is expected to get even higher in the future. This is a significant claim, as 20% efficiency is typical among solar panels which use more expensive materials." Scrolling down. Ooh, let's look at growth. I'm a real fan of solar panels. I haven't gotten any yet. I don't live by myself just yet, helping take care of the grandparents. So I'm not able to make energy decisions as of yet. But once on my own, it is in the 5-year plan to have a house that's completely at least 80% energy efficient. And the idea is solar panels. Take a sip of tea here. Solar photovoltaics is growing rapidly. Solar is kind of an odd grammar structure there. Solar photovoltaics is growing rapidly. Sounds like it should be R, shouldn't it? That's the thing between European, British English and American English. You will refer to a group with either singular or plural. You would say, for instance, the class is, so, and or the class are. So I think in British English they say, like, the class are being rowdy right now, because there are multiple kids in the classroom, versus American, the class is. Although I guess the convention here doesn't make sense either way. Solar photovoltaics are growing rapidly, and worldwide installed capacity reached about 300 gigawatts by the end of 2016. That sounds more accurate. So that's what I'm going to say. They are growing rapidly, and they reached a capacity of about 300 gigawatts by the end of 2016. Since 2000, installed capacity has seen a growth factor of about 57. The total power output of the world's PV capacity in a calendar year in 2014 is now beyond 200 terawatt hours of electricity. This represents 1% of worldwide electricity demand. More than 100 countries use PV. China, followed by Japan and the United States, is now the fastest growing market, while Germany remains the world's largest producer, contributing more than 7% to its national electricity demand. That's pretty interesting. And that's a kind of optimistic how much it's grown. I'm looking at a graph here, the worldwide growth of photovoltaics on a semi-log plot since 1992, where in 1992 it looks like you have next to no gigawatts. By 1997, or it looks like about 2000, you crest about 1 gigawatts. You crest to 10 gigawatts in 2007, 100 in 2012, and right now in 2018 we are well on our way to 1,000 gigawatts, which is not too shabby, but we could do better, and I think we will. Several market research and financial companies foresee record-breaking global installation of more than 50 gigawatts in 2015. I guess this was written earlier. China is predicted to take the lead from Germany and to become the world's largest producer of PV power by installing another targeted 17.8 gigawatts in 2015. So this article hasn't been updated for a few years, referring to 2015 in the future sense. By 2018, worldwide photovoltaic capacity is projected to double or even triple to 430 gigawatts. Solar Power Europe, formerly known as the EPIA, also estimates that photovoltaics will meet 10 to 15% of Europe's energy demands by 2030. That's pretty good. That's not bad, especially with breakthroughs in technology, the price going down. Let's see. One thing I've always been curious about are how solar. Let's scroll back up. We're going to click on solar panels. We're going to look at a very, more specific. Solar panels are one energy source within the greater photovoltaic energy gathering method. Solar panels, or photovoltaic solar panels, absorb sunlight as a source of energy to generate electricity. A PV module is a packaged connected assembly of typically 6x10 photovoltaic solar cells. Photovoltaic modules constitute the photovoltaic array of a photovoltaic system that generates and supplies solar electricity in commercial and residential applications. Each module is rated by its DC output power under standard test conditions and typically ranges from 100 to 365 watts. The efficiency of a module determines the area of a given the same rated output. An 8% efficiency of 230 watt module will have twice the area of a 16% efficiency at 230% 230 watt module. So hang on. The efficiency of a module determines 8% efficient. Oh, okay, I see. So in order to reach the same 8%, will have to be double. That makes sense. There are a few commercially available solar modules that exceed efficiency of 24%. I'm sure those are probably very expensive. And while I don't doubt their capabilities, they're probably for people with more limited space. Think about living in the city, not very much yard. And for them, probably a good option because people living in cities, owning property in cities, tend to have more income because cities will pay workers more, just cost of living. Let's see how the price of solar power has continued to fall so that in many countries it is cheaper than ordinary fossil fuel electricity from the electricity grid, a phenomenon known as grid parity. And here's the content. We're going to scroll down. Let's see. Let's look at theory and construction. Photovoltaic modules use light energy from the sun to generate electricity through the photovoltaic effect. The majority of modules use wafer-based crystalline silicon cells, or thin film cells. The structural load-carrying member of a module can either be the top layer or the back layer. Cells must also be protected from mechanical damage and moisture. Most modules are rigid, but semi-flexible ones based on thin film cells are also available. The cells must be connected electrically in series, one to another. Externally, most of photovoltaic modules use MC4 connectors type to easy weatherproof connections to the rest of the system. We'll scroll down a little bit and go to the efficiency. Depending on construction, photovoltaic modules can produce electricity from a range of frequencies of light, but usually cannot cover the entire solar range, specifically ultraviolet, infrared, and lower diffuse light. Hence, much of the incident sunlight energy is wasted by solar modules, and they can give far higher efficiencies if illuminated with monochromatic light. Now that's interesting and something I did not know. Monochromatic light is more advantageous to solar panels or photovoltaics because they're only able to gather, I guess, within a specific range. So those of you listening and wishing to be inventors, if you can find a way to split the light up on a small scale and have, like, maybe I guess make little tiny prisms, but direct all of, let's say, the ultraviolet to one side and all of the infrared to another, then you could, I guess, in theory, create a way more efficient solar panel that uses sunlight. Therefore, another design concept is to split the light into 6 to 8 different wavelength ranges that will produce a different color of light and direct the beams onto different cells by turning to those ranges. This has been projected to be capable of raising efficiency by 50%. See? That's amazing. 50% efficient energy gathering. Granted, I'm sure that's not commercially viable yet and probably won't be for some time, but those of you listening, if you can figure out a way to do that, my God, go ahead and do that and make yourself a nice, cool few $1 billion there. Scientists from Spectrolab, a subsidiary of Boeing, have reported development of multi-junction solar cells with an efficiency of more than 40%, a new world record for solar photovoltaic cells. The Spectrolab scientists also predict that concentrator cells could achieve efficiencies of more than 45% or even 50% in the future, with theoretical efficiencies being about 58% in cells with more than 3 junctions. That's pretty cool. Currently, the best achieved sunlight conversion rate is around 21.5% in new commercial products, typically lower than the efficiencies of their cells in isolation. That makes sense. In test conditions, you're going to get a lot better than in the real world applications, at least for this sunlight gathering, because the sunlight is many wavelengths of light. The most efficient mass-produced solar modules have power density values of up to 175 watts per meter squared, or 16.22 watts per foot squared. So, because I'm American garbage, I'm going to use foot, and also because it's a little bit easier to see with the webcam. So you got a square foot like that, and every single square foot like that is going to be 16.22 watts. If you wanted to get up to 32.44 watts, you need 2 of those bad boys. If you wanted 64.88, you got to get 4, and so on and so forth. Let's scroll down a little bit and see technology, because I know that the technology has definitely grown and just gotten a lot better. And I'm looking at a graph here, and again, a lot of the podcasts I'll just describe visually. It shows the global market share by photovoltaic technologies. And so in the early 90s, almost all photovoltaic technologies were monosilicates. But then you had there were also, during this time, ribbon silicates, slightly thin film experimentations, and multisilicates. Multisilicates began to grow and overtake monosilicates. Thin films expanded, then contracted. And it seems like right now multisilicates are where most people are concentrating. So let's read about the technologies. Most solar modules are currently produced from crystalline silicon solar cells made of multicrystalline and monocrystalline silicon. In 2013, crystalline silicon accounted for more than 90% of worldwide photovoltaic production, while the rest of the overall market is made up of thin film technologies using cadmium telluride, CIGS, and amorphous silicon. Let's click on cadmium telluride. I don't know what that is, but maybe we can find out. Cadmium telluride photovoltaics describes a photovoltaic technology that is based on the use of cadmium telluride, a thin semiconductor layer designed to absorb and convert sunlight into electricity. Cadmium telluride PV is the only thin film technology with lower cost than conventional solar cells, made of crystalline silicon in multi-kilowatt systems. On a life cycle basis, CDTE PV, say that 5 times fast, has the smallest carbon footprint, lowest water use, and shortest energy payback time of all solar technologies. CDTE's energy payback time of less than a year allows for faster carbon reductions without short-term energy deficits. So that's pretty advantageous. Let's scroll down to materials and see what it uses. Cadmium, a toxic heavy metal considered a hazardous substance, is a waste byproduct of mining, smelting, and refining sulfide ores of zinc during zinc refining, and therefore its production does not depend on PV market demand. Okay, so that's good. Cadmium, we're going to have that regardless. Tellurium production and reserves estimates, and this is, I'm kind of skipping around. I'm reading about tellurium now. Tellurium production and reserve estimates are subject to uncertainty and vary considerably. Tellurium is a rare, mildly toxic metalloid that is primarily used as a machining additive to steel. Te is almost exclusively obtained as a byproduct of copper refining, with smaller amounts from lead and gold production. Only a small amount, estimated to be about 800 metric tons per year, is available. According to USGS, which is the United States Geological Survey, global production in 2007 was 135 metric tons. 1 gigawatt of CDTE PV modules will require about 93 metric tons at current efficiencies and thickness. Though improved material efficiency and increased PV recycling, the CDTE PV industry has the potential to fully rely on tellurium from recycled end-of-life modules by 2038. In the last decade, new supplies have been located in Hsinchu, China, as well as in Mexico and Sweden. In 1984, astrophysicists identified tellurium as the universe's most abundant element, having an atomic number over 40. It's kind of a very specific category, but itself very fascinating. Why is tellurium more abundant? That's pretty interesting. Certain undersea ridges are rich in tellurium. Let's scroll back up. Let's look up at zinc refining, because I love me some zinc. Who doesn't? And I want to know how they refine it. Zinc refining is a process of purifying zinc to super high-grade zinc, which is at least 99.995% pure. This process is not usually required. Smelting of zinc is done through electrolysis process, but is needed when zinc is produced by pyrometallurgical processes, because it is only 98.5% pure. I'm going to take a sip of tea. There are various refining methods, but the refluxing process is the most commonly used. High purity zinc is required industrially to avoid zinc pest, a slow distortion and cracking of zinc die castings caused by impurities precipitating out. From here, let's click on cadmium because it talks about byproducts. And we just read a little bit into cadmium. Cadmium is a chemical element with symbol CD and atomic number 48. This soft, bluish-white metal is chemically similar to the two other stable metals in group 12, namely zinc and mercury, which I guess is why they hang out together. Like zinc, it demonstrates oxidation state +2 in most of its compounds, and like mercury, it has a lower melting point than the transition metals in group 3 through 11. Cadmium and its congeners in group 12 are often not considered transition metals, in that they do not have partly filled D or F electron shells in the elemental or common oxidation states. Okay, so there was a lot to take in there. Essentially what it's saying is, because when you measure elements, when you look at elements on the periodic table, the further down you go, that is, the bigger the atomic number, the more electrons you can expect. And that makes sense, because hydrogen, having one proton, is only going to have a mildly positive charge. So it's only going to attract one little electron. Helium, having 2 protons, will have twice the charge and can have 2 electrons. Now, we just mentioned that cadmium, being number 48, has 48 protons. So that means that you'd expect for it to be for it to have 48 electrons, which, and it could differ depending on where it's located, but these electrons have to be somewhere, and we call these somewhere shells. And I don't remember the exact numbers of the shells, but the further out you go, D and F are kind of shells that are further out. Essentially science. It gets a little complicated. Not difficult, but complicated when you start studying it. And the difference between difficult and complicated is it's very, very, very difficult for a person to swim across the Atlantic Ocean. It's very, very, very complicated for him to navigate a ship across there, to build a ship and navigate. It's because building a ship, It's complicated because there's a lot of tiny little steps involved, but it's not difficult because those are tiny steps and each step is surmountable. Anyway, I digress. Let's continue with cadmium here. Ooh, I'm scrolled down to the contents. History. Dare I click it? I'm going to click it. Let's look up the history. The reason I'm willing to do so is because I know that we're not going to delve too far back. Cadmium, Latin cadmium, was discovered simultaneously in 1817 by Friedrich Stromeyer and Samuel Leberecht Hermann, both in Germany, as an impurity in zinc carbonate. Stromeyer found the new element as an impurity in zinc carbonate, and for 100 years, Germany remained the only important producer of the metal. The metal was named after the Latin word for calamine because it was found in the zinc ore. Stromeyer noted that some impure samples of calamine changed color when heated, but pure calamine did not. He was persistent in studying these results and eventually isolated cadmium metal by roasting and reducing the sulfide. The potential for cadmium yellow as a pigment was recognized in the 1840s, but the lack of cadmium limited its application. Even though cadmium and its compounds are toxic in certain forms and concentrations, the British Pharmaceutical Codex from 1907 states that the cadmium iodide was used as a medication to treat enlarged joints, scrofulous glands, and chilblains. In 1907, the International Astronomical Union defined the international angstrom in terms of a red cadmium spectral line, where one wavelength equals 6,438.46963 angstroms. This was adopted by the 7th General Conference on Weighted Measures in 1927. In 1960, the definitions of both the meter and angstrom were changed to use krypton, and that makes sense because krypton is a lot less reactive of a gas. Okay, so I'm going to click on krypton, and I know everybody knows about krypton because of kryptonite and Superman and planet Krypton. Krypton is actually also a noble gas, and it's very interesting, the noble gases, because they're extremely unreactive. You've got some gases like hydrogen and oxygen and nitrogen, which appear in all sorts of compounds. H2O, for instance, H2O2. Oxygen, hydrogen, nitrogen, all these guys like to bond with other elements. The noble gases are very, very difficult and very seldomly bond. And krypton is one of them, so let's read about them. Krypton is a chemical element with the symbol Kr and atomic number 36. It is a member of group 18, the noble gases, elements. A colorless, odorless, tasteless noble gas, krypton occurs in trace amounts in the atmosphere, often used with other rare gases and fluorescent lamps. With rare exceptions, krypton is chemically inert. Krypton, like other noble gases, is used in lighting and photography. Krypton light has many spectral lines, and krypton plasma is useful in bright, high-powered gas lasers, each of which resonates and amplifies a single spectral line. Krypton fluoride also makes a useful laser. From 1960 to 1983, the official length of a meter was defined by the 605 nanometer wavelength of the orange spectral line of krypton 86 because of the high power and relative ease of the operation of krypton discharge tubes. That was a mouthful. What that was essentially saying is that from 1960 to 1983, they would define the meter in terms of a physical constant. Or, well, they've been trying to define the meter in terms of a physical constant. And from 60 to 83, they chose the 605 nanometer wavelength of the orange spectral line of krypton 86. Essentially what they were going to do is probably use the energy and wavelength of it to measure the meter. So a meter is X number of these wavelengths, if that makes sense. The krypton was discovered in Britain in 1898 by Sir William Ramsay, a Scottish chemist, and Morris Travers, an English chemist. and residue left over from evaporating nearly all compounds of liquid air. Neon was discovered by a similar procedure by the same workers just a few weeks later. And neon is another Nobel gas, by the way. William Ramsay was awarded the 1904 Nobel Prize in Chemistry for discovering a series of noble gases, including krypton. In 1960, the International Conference on Weights and Measures defined meter as 1,650,763.73 wavelengths of light emitted by the krypton-86 isotope. This agreement replaced the 1889 International Prototype Meter located in Paris, which was a metal bar made of platinum-iridium alloy, one of a series standard. Let's look up the International Conference on Weights and Measures. I know that there's actually a fascinating history with them, because when we talk about things like the foot and the meter and the mile and the kilometer, we're talking about distances. Well, you have to set these distances to something. Now, we all have tape measures and what have you, but what are those tape measures set by? Well, the factory decides. How does the factory decide? Well, they looked it up. Where did they look it up from? Well, probably there's an organization that exists, and this is the organization, by the way, International Bureau of Weights and Measures. Well, how did they define it? How do you define things? That's a really good question. The International Bureau of Weights and Measures is an intergovernmental organization established by the Meter Convention, through which member states act together on matters related to measurement science and measurement standards. The organization is usually referred to by its French initialism, BIPM. The BIPM's headquarters is based at Sèvres, France. It has custody of the International Prototype Kilogram and houses the secretariat for this organization, as well as hosting its formal meetings. So let's look up the International Prototype Kilogram. Or, well, hang on, we'll scroll down. Yeah, let's look up the International Prototype Kilogram. We need to figure out who's deciding what the kilogram is. Who knows? Maybe they'll change it. They changed it one day. So I clicked on the article, and it took me to the kilogram, and then the contents below, the International Prototype Kilogram. Since 1889, the magnitude of the kilogram has been defined as the mass of an object called the International Prototype Kilogram, often referred to in professional metrology as the IPK. The IPK is made of a platinum alloy known as PT10IR, which is 90% platinum and 10% iridium by mass, and is machined into a right circular cylinder where the height and diameter are equal, of about 39 millimeters, to minimize its surface area. The addition of 10% iridium improved upon the all-platinum kilogram of the archives by greatly increasing the hardness, while still retaining the platinum's many virtues, such as extreme resistance to oxidation, extremely high density, which is almost twice as dense as lead and more than 21 times as dense as water, satisfactory electrical and thermal conductivities, and low magnetic susceptibility. The IPK and its 6 sister copies are stored in the International Bureau of Weights and Measures in an environmentally monitored safe in a lower vault located in the basement of the BIPM's Pavillon des Breteuils in St. Cloud. On the outskirts of Paris, 3 independently controlled keys are required to open the vault. Official copies of the IPK were made available to other nations just as their national standards. These are compared to the IPK roughly every 40 years, thereby providing traceability of local measurements back to the IPK. So this is some serious business here. These international prototype kilograms are the basis for what a kilogram is. So if you were to go there, let's say, and nick a little bit of it off the top, you've all of a sudden changed what a kilogram is. Now, they're going to know that something's amiss here, and they have other copies floating around the world, and they will rectify the decision. But it's a very important trying to keep it all straight. The Meter Convention was signed on the May 20th of 1875 and further formalized the metric system, quickly leading to the production of the IPK. The IPK is one of 3 cylinders made in 1879 by Johnson Matthey, which continues to manufacture nearly all of the national prototypes today. In 1883, the mass of the IPK was found to be indistinguishable from that of the Kilogramme des Archives, made 84 years prior, and was formally ratified as the kilogram by the first CGPM in 1889. Modern measurements of Vienna Standard Mean Ocean Water, which is pure distilled water with an isotopic composition representative of the average of the world's oceans, show that it has a density of 0.999975 plus or 1 minutes of a kilogram per liter at its point maximum density under 1 standard atmosphere of pressure. Thus, a cubic decimeter of water at its point of maximum density is only 25 parts per million less massive than the IPK. That is to say, the 25 milligram difference shows that the scientists over 219 years ago managed to make the mass of the kilogram of the archive equal to that of a cubic decimeter of water at 4 degrees Celsius, with a margin of error at most within the mass of a single excess of grain of rice. That's fascinating. A decimeter. That is, first of all, a cubic decimeter is huge. A cubic decimeter is 10 meters by 10 meters by 10 meters, which is about 30 feet by 30 feet it's more than 30 feet. So it'd be about 33 feet by 33 feet by 33 feet. And fill that full of ocean water. Make sure that that water is at 4 degrees Celsius and at standard temperature or standard pressure, atmospheric. And the precision of that is a single grain of rice inside that water, different than what they set the kilogram equal to. The kilogram's not that heavy, but if you had that much water and you measured it versus that many kilograms, which is amazing that 219 years ago, in an era when we were still trying to figure out the germ theory of disease, they had measurements that precise. So let's look up copies of the International Prototype Kilogram. The various copies of the International Prototype Kilogram are given the following designations in the literature. The IPK itself, located in St. France. 6 sister copies, located in St. Cloud, France. 10 working copies, 8 for routine use and 2 for special use, located in St. Cloud, France. National prototypes stored in, and then they give a large number of countries. And some of these countries have multiples. United States, we're rocking 5 of these bad boys. The UK, how can they even compete? They've only got 3. Some additional copies held by non-national organizations, such as the French Academy of Sciences in Paris. Let's look up the stability, and this is fascinating because all elements, no matter how stable they supposedly are, aren't actually 100% stable. Even the proton, which is the fundamental basis for all atoms, and you say, oh, but what about quantum? Okay, but you know what I mean. Even the proton, which is like the particle, has a half-life of like 10 to the 41 years, which is a lot, but it still decays. So by definition, the error in the measured value of the IPK's mass is exactly 0. The mass of the IPK is the kilogram, meaning that if the IPK fluctuates, then it's the rest of the world that's changed. However, any changes in the IPK's mass over time can be deduced by comparing its mass to that of its official copy stored throughout the world, a rarely undertaken process called the periodic verification. The only 3 verifications in 1889, 1948, and 1989. For instance, does that mean that we are in 2048 going to have another union? For instance, the U.S. owns 4 90% platinum, 10% iridium kilogram standards, 2 of which, K4 and K20, are from the original batch of 40 replicas delivered in 1884. The K20 prototype was designated as the primary national standard for mass of the United States. Both of these, as well as those from other nations, are periodically returned to the BIPM for verification. Extraordinary care is exercised when transporting prototypes. In 1984, the K4 and K20 prototypes were hand-carried in the passenger section of separate commercial airlines. So it might sound funny to those of you listening that they're taking these weights and having to keep them under lock and key. The IPK itself requiring 3 separate keys from 3 separate individuals locked in the vaults under France. But this is serious. When they flew these 2 prototypes out in separate airliners, this is serious. If something happened to one of those airlines, then you're going to have to create another, I guess, American kilogram, because you're still going to have little differences between the IPK and what we have. And creating that's going to cause, you're going to have to weigh the original, mass the original, and it's going to cause, it's a big deal. Just a big deal. Note that none of these replicas has a mass precisely equal to that of the IPK. Their masses are calibrated and dotted as offset values. For instance, K20, the US's primary standard, originally had an official mass of 1 kilogram per 39 micrograms in 1889, which is to say K20 was 9 kilograms less than the IPK. A verification performed in 1948 showed the mass of 1 kilogram minus 19 micrograms. The latest verification performed in 1989 shows a mass precisely identical to its original 1889 value. Quite unlike transient values such as this, the US's Czech standard K4 has persistently declined in mass relative to the IPK. And for an identifiable reason, Czech standards are used much more often than primary standards and are prone to scratches and other wear. K4 was minus 75 micrograms in 1889, but as of 1989 was officially calibrated at 6 micrograms less, and 10 years later 116 micrograms less. Over a period of 110 years, K4 lost 41 micrograms to the IPK. So that's pretty interesting in itself, that measuring these and setting them equal to, like, oh, well, let's find out how much this one has changed compared to our standard. Well, when you measure them and mass them, you are doing so, and you're going to handle them, and even the slightest touch is going to shave off tiny little atoms. Beyond the simple wear that Czech standards can experience, the mass of even the carefully stored national prototypes can drift relative to the IPK for a variety of reasons, some known and some unknown. Since the IPK and its replicas are stored in air, albeit under 2 or more nested bell jars, mass through absorption of atmospheric contamination onto their surfaces. So molecules bonding with the surface molecules of the kilograms. Luckily, they are cleaned in a process the BIPM developed between 1939 and 1946, known as the BIPM cleaning method, that comprises firmly rubbing with a chamois soaked in equal parts ether and ethanol, followed by steam cleaning with bi-distilled water, and allowing the prototypes to settle for 7 to 10 days before verification. That's fascinating. Before the BIPMs, it blows my mind. They have, how are you going to clean these? And they've found a way. But man, I can't imagine of having to clean one of these. Before the BIPMs published reports in 1994 detailing the relative change in mass of the prototypes, different standard bodies used different techniques to clean their prototypes. The NIST's practice before then was to soak and rinse its 2 prototypes first in benzene, then in ethanol, and then to clean them with a jet of bi-distilled water steam. Cleaning the prototypes removes between 5 and 60 micrograms of contamination, depending largely on the time elapsed since the last cleaning. Further, a second cleaning can remove up to 10 micrograms more. After cleaning, even when they were stored under their bell jars, the IPK and its replicas immediately begin gaining mass again. The BIPM even developed a model of this gain and concluded that it averaged 1.11 micrograms per month for the first 3 months after cleaning, and then decreased to an average of 1 microgram per year thereafter. So the first 3 months you're going to gain about 3 1/3 micrograms, and then after that 1 microgram per year. Since check standards are like K4 are not clean for routine calibration mass standards, a precaution to minimize the potential wear and handling damage, the BIPM's model of time-dependent mass gain has been used as an after-cleaning correction factor. This all is just incredibly fascinating because, my gosh. Well, let's look up I could sit here and read this all day but I got to skip around. So let's jump down to the proposed future definitions for the SI unit. I'm going to take a sip of tea while I kind of peruse here really quick. That's good. So it seems like there are some controversies with how the kilogram is weighed and everything. And let's see. It says that the SI, one of the approaches they want is an atom counting approach. So you take an atom with a known mass, count out that many atoms, and then set that equal to a kilogram. So carbon-12, though not offering a practical realization, this definition would precisely define the magnitude of the kilogram in terms of a certain number of carbon-12 atoms. And that makes sense because no matter where you are in the world, carbon-12 atom is going to weigh the same in France as it is in America, no matter what atmospheric contaminants. So all you got to do is get X number of those, and then boom. The mole is currently defined as the quantity of entities equal to the number of atoms in 12 grams of carbon-12. So carbon-12 is already used as a basis for one set of measurements. Thus, the current definition of the mole requires that 1,000 over 12 moles, or 83 moles of carbon-12, will have a mass of precisely 1 kilogram. The number of atoms in a mole, a quantity known as the Avogadro constant, is experimentally determined, and the current best estimate of its value is, and they've got a long string, I'm just going to read the first few digits, 6.022 times 10 to the 23rd entities per mole. This new definition of the kilogram proposed to fix the Avogadro constant precisely at 6.02214 x times 10 to the 23rd, with the kilogram being defined as the mass equal to that of 1,000 over 12 times Avogadro constant atoms of C12. The accuracy of the measured value of the Avogadro constant is currently limited by the uncertainty in the value of the Planck constant. Let's click on Planck constant. I know a little bit about it. I know that it is used in determining quantum issues. But let's look a little bit more about it, because I only know it as a number represented by the letter H. The Planck is a physical constant that is the quantum of action, central in quantum mechanics. First recognized in 1900 by Max Planck, it was conceived as the proportionality constant between the minimal increment of energy, E, of a hypothetical electrically charged oscillator in a cavity that contains blackbody radiation, and the frequency, F, of its associated electromagnetic wave. So essentially, it's a ratio determining the frequency of a charge to its energy. It's pretty standard. In 1905, the value of E, the minimal energy increment of a hypothetical oscillator, was theoretically associated by Albert Einstein with a quantum, or minimal element, of the energy of the electromagnetic wave itself. So let's look up the origins, and we'll click on blackbody radiation. Because I remember this was a big issue back in the day. They had a problem. In the last years, and we'll see if they talk about this problem. In the last years of the 19th century, Planck was investigating the problem of blackbody radiation, first proposed by Kirchhoff some 40 years earlier. It is well known that hot glow, and that hotter objects glow brighter than cooler ones. The electromagnetic field obeys laws of motion similar to mass on a spring, and can come to equilibrium with hot atoms. The hot object in equilibrium with light absorbs just as much light as it emits. If the object is black, meaning it absorbs all the light that hits it, then its thermal light is maximized. The assumption that black body radiation is thermal leads to an accurate prediction. The total amount of emitted energy goes up with the temperature, according to a definite rule, the Stefan-Boltzmann law. But it was also known that the color of light given off by a hot object changes with the temperature, so that white hot is hotter than red hot. Nevertheless, Wilhelm Wien discussed a mathematical relationship between the peaks of the curves at different temperatures by using the principle of adiabatic invariance. At each different temperature, the curve is moved over by Wien's displacement law. Wien also proposed an approximation for the spectrum of the object, which was correct at high frequencies, but not at low frequencies. It was still not clear why the spectrum of a hot object had the form that it has. So they're trying to figure out the law with figuring out colors of an object versus its temperature. Planck hypothesized the equations of motions for light described a set of harmonic oscillators, one for each possible frequency. He examined how the entropy of the oscillators varied with the temperature of the body, trying to match Wien's law, and was able to derive an approximate mathematical function for blackbody spectrum. However, Planck soon realized that his solution was not unique. There were several different solutions, each of which gave a different value for the entropy of the oscillators. To save his theory, Planck had to resort to using the then controversial theory of statistical mechanics, which he described as an act of despair. I was not ready to sacrifice any of my previous convictions about physics. I was ready to sacrifice. One of his new boundary conditions was to interpret the vibrational energy of n oscillators not as an infinitely divisible quantity, but as a discrete quantity composed of an integral number of finite equal parts. Let us call each such part the energy element E. So essentially, this is a long-winded way to figure out the Planck-Einstein relation where E equals hf. So energy equals the Planck constant times frequency. Prior to Planck's work, it had been assumed that the energy of a body could take on any value whatsoever, that it was a continuous variable. The Rayleigh-Jeans law makes close sense for a narrow range of values at one limit of temperatures, but the results diverge more and more strongly as temperatures increase. So Rayleigh-Jeans had one set of theories about how to measure the temperatures and energies of a frequency, and then Wien had a different one, and both of their values worked at different temperatures, but there was no quite right variable between there was no connecting the two. To make Planck's law, which correctly predicts blackbody emissions, it was necessary to multiply the classical expression by a complex factor that involves h in both the numerator and denominator. The blackbody problem was revisited in 1905 when Rayleigh and Jeans, on the one hand, and Einstein on the other hand, independently proved that classical electromagnetism could never account for the observed spectrum. These proofs are commonly known as the ultraviolet catastrophe, a name coined by Paul Ehrenfest in 1911. They contributed greatly, along with Einstein's work on the effect, in convincing physicists that Planck's postulate of quantized energy levels was more than a mere mathematical formalism. The very first Solvay conference in 1911 was devoted to the theory of radiation in quanta. Max Planck received the 1918 Nobel Prize in Physics in recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. Okay, so this is a very, very complicated, long article, which used a lot of terms. Essentially, you had when you heat an object up, it starts to glow, and when you heat it up more, it starts to glow more. At those lower heated temperatures, you had laws that kind of worked. Rayleigh-Jeans law. But then they stopped working the hotter they got. On the opposite end, you had Wien's law. they worked really hot, but when you got cold, it didn't quite work. To reconcile the two, you have to have a theory where you treat light as a wave, but not just a wave, as a particle too. The quanta that they mentioned was the word that was originally given to photons, I believe. And you treat the frequency like an oscillation, and by doing so, you have essentially he treated light as a different thing, and energy as a different thing than what had previously been governed and discussed. And because he had done that, he was able to figure out the issue with the black body radiation. And I'm going to really quick go to the Wikipedia article. A black body is an idealized physical body that absorbs all incident electromagnetic radiation, regardless of frequency, angle, or incidence. So when they were discussing that, they were talking about ideal conditions. And let's see. An ideal black body in thermal equilibrium has two noticeable properties. It is an ideal emitter. At every frequency, it emits as much or more thermal radiative energy as any other body at the same temperature. So nothing emits better than it. It is a diffuse emitter. The energy is radiated isotropically, independent of direction. And that just means that it doesn't emit in a single direction. And then, gosh, looking at the time, it's about time to call this one quits. So what did we learn today? Summarizing, and I'll discuss the physics a little bit better here. Well, we started off with photovoltaics, the materials and energy gathering methods that use and convert light into electricity. One of those being, and we looked up the current developments of photovoltaics, and we found that they are developing pretty well, that they've got some more technology and they expect better efficiencies in the future. We clicked on solar panel, and we learned about how the solar panels absorb sunlight. They have a certain grid, and they've got different methods, mostly using silicon. One of those methods uses cadmium telluride photovoltaics, and we learned that this is a way of gathering energy. But from there, curiously, looked up, and it talked about cadmium being a toxic heavy metal in zinc refining, and tellurium being a toxic metalloid that is primarily used added to steel. This was tellurium, by the way, is the element over atomic number 40, which is most common in the universe. It was odd. From there, we looked up zinc refining. We found that the zinc mining and refining process requires you to get it to 99.995% efficiency. From there, and is a byproduct of this. So we clicked on cadmium, and we spent some time reading a little bit about our good friend cadmium, which is a toxic element in group 12, along with zinc and mercury, and with a atomic number of 48. And because I'm pretty tempted by these things, I saw history, and I clicked on the history, and I learned that in 1817 it was discovered independently by both Frederick Strohmeyer and Carl Samuel Lebrecht Hermann, both in Germany. And that they found these as a result of experimenting with zinc. From there, we learned a little bit about Krypton, and it's not just a planet in Superman's world, an X-planet, I should say, but it's also a noble gas, which noble gases do not bond well with other elements, and because of that, they're very, very, very inert. From Krypton, because we kept coming across this one term, the General Conference on Weights and Measures, and the International Bureau of Weights and Measures. We clicked on that, and we learned that there's actually a society organized to discuss how much things, the measurement of things, and they base these off of a single, I guess you could call it frame of reference. And even if this frame of reference changes, they just consider it the same thing. So, for instance, we clicked on the International Prototype Kill, and we learned that this thing was the International Prototype Kilogram was created way back in the 1800s. Copies were made, given to America, but the single kilogram, the IPK, International Prototype Kilogram, is kept under lock and key in a vault in France, and it requires 3 independent keys to open, and that any changes to it don't matter. It's still considered the kilogram. All other kilograms will have changed as a result. And that copies in America, when they were sent to kind of recalibrate, measure the IPK versus the copies, it's such a big deal that our copies were sent on 2 separate planes. There were our proposed future definitions, setting it equal to carbon-12 and counting the number of atoms. It's because, again, carbon-12, the atoms are going to weigh the same over here as they do there. But that's kind of it's a little unrealistic. From there, we learned that there would still be differences because of issues with the Planck constant and on the Planck scale, and on Planck constant, and learned that it's the constant that you use to figure out the relationship between the frequency of a blackbody emitter or electromagnetic wave versus its energy. Find a light, the frequency of that light versus the energy within that light. The relationship is thanks to the Planck constant. And then we learned that this helped solve a blackbody radiation problem where you couldn't quite figure out the temperature relationship versus the color. This didn't work on the blackbody for some reason. So if I shined a light, you can figure that out with Planck constant. You couldn't do that if you heated something up. So if I heated something up, if I shined a red light, you can figure out, okay, frequency of a red light, it has this energy. Boom. But if you heated something up until you had that same frequency of red light, you're going to have a bit of a problem. And they figured that out with, and Planck won the Nobel Prize for it. Big hero. And we learned that the black body is an idealized physical body that absorbs all electromagnetic radiation, regardless of frequency or angle of incidence, and that nothing emits it better than a black body, and that it emits it in all sorts of directions. Kind of confusing. I stare a little bit at the end. But I think that does it for our Wikiclick podcast. Thank you guys so much for listening, and hope to see you again soon. Bye.